Okay, we're now in our example number 2 for the topic related rates problem. A burn on a person's skin is in the shape of a circle. If the radius of the burn is decreasing at the rate of 0.05 centimeters per day, when it is 1.0 centimeter, what is the rate of decrease of the area of the burn at that instant? Okay, again, we need to analyze the problem now and make sure that we understand the problem. And at the same time, we identify the given quantities, okay? We're talking about circular burn, okay, on a person's skin. That's a geometric concept, geometric figure. So we have radius here, which we again denote by R. And aside from that, it says here that the radius, no, of the burn is decreasing at the rate of 0.05 centimeter per day. So again, we have here the rate of change of the radius with respect to time, okay? Or we denote that by dr dt. So for our first given value, we have dr dt equals, now we use negative because the rate is decreasing. Okay, this is decreasing at the rate of 0.05 centimeter per day. That's why we have negative 0.05 centimeters per day. When it is 1.0 centimeter, okay, that's again another value. That's the value for the radius, no? It means that's the starting radius. So include that as our given. R is equal to 1.0 centimeter. Of course, this radius is changing, right? It is decreasing. Starting from 1.0, it is decreasing at the rate of 0.05 centimeters per day. Okay, question. What is the rate of decrease of the area of the burn at that instant? So what are we looking for here? We're looking for the rate of decrease of the area of the burn. It means another quantity we have here is the area, and the area is changing again with respect to time. And when we say what is the rate of decrease of the area, this is denoted by D. If we use A for the symbol as our notation for the area, then rate of decrease of the area is dA dt, right? Okay. And take note that we have here a geometric figure, okay? So we have a circle, and we know that the area of a circle is given by pi r squared. So we start with that, okay? A equals pi r squared. Again, A and R are functions of time. Finding dA dt means we have to compute for the derivative of both sides with respect to time using the chain rule. So we'll have this, okay? The derivative of A equal to the derivative of pi r squared with respect to time. And what is the derivative of A with respect to time? It would be dA dt. While pi here is constant, we can take it out of the d dt. And then the derivative of r squared is 2r using the chain rule, no? 2r times the derivative of r, which is dr dt. And since we're looking for the dA dt, okay, we can write this in simpler form as dA dt equals 2 pi r dr dt, right? Okay, and then let's see if we can find the rate of decrease of the area with respect to time is R given. We have R here. What about dr dt? We also have dr dt. So we just plug in these given values to the resulting expression. Then we have this, right? 2 pi times r, which is 1.0. And then dr dt is negative 0.05 centimeter per day. Simplifying, this will become centimeter squared. No? We have negative 0.01 pi square centimeter per day. Again, what do you mean by this? It means that the area is decreasing. Okay, the area of the burn is decreasing at the rate of 0.01 pi square centimeter per day. Okay, so that's our second example. Now for the third example, we have another interesting problem here. Cylindrical tank with radius 5 meters is being filled with water at a rate of 3 cubic meter per minute. 3 cubic meters per minute. How fast is the height of the water increasing? Okay, so let's analyze this very carefully. So you have a cylindrical tank, okay, with radius 5 meters. This is being filled with water, okay, at the rate of 3 cubic meters per minute, meaning every minute the volume is you are adding 3 cubic meter per minute now to the volume of the water. Okay. Then how fast is the height of the water increasing? Okay. First, let's assign some notations. Okay, for the quantities here. We have the radius, so we denote that by r. That's actually our first given there. Radius or r is 5 meters. And we have a rate of 3 cubic meters per minute. It refers to what? It refers to the volume, no? It refers to the volume of the water. You can see here the unit of measurement, okay? Cubic meter, that refers to the volume per minute. And at a rate of 3 cubic meters per minute, that refers to the dvdt or derivative of the volume with respect to time, because the volume here is changing per unit time. Okay. Then we're going to find the height. Okay. We're not the height, but we're going to find for the derivative of the height with respect to time. Why the derivative of the height? Because it says here how fast is the height of the water increasing. So that's again the change in height, no, per unit time. So when you say how fast is the height of the water increasing, that means what is the derivative of the height with respect to time for the dh dt. Again, we want an expression that we can utilize here, since we have a cylinder. This is a cylindrical tank. From your geometry again, what is the volume of the cylinder? It's actually pi r squared times height, right? Okay, pi r squared times height. Pi r squared is the area of this one here times the height. So that's the volume. Okay. Now again, the volume, and the h are functions of time. What about the r? Is r also a function of time? No, it's not a function of time because R is a fixed value. It's not affected by the change in the value with respect to time. No, only the volume changes with respect to time, and also the height changes with respect to time. The height here is the height of the water, not the height of the tank. Okay, but the height of the water. That's why the height changes with respect to time. Also, the volume changes with respect to time. But R is fixed. It's not changing because even if the height of the water changes or the volume of the water changes, your R remains the same. The radius is the distance from the center here, no, to the edge, okay, of the cylinder. Okay, so that's why this is fixed. With that, we obtain the a working formula by substituting your R to the equation. Okay, so you have V equals pi times 5 meter quantity squared times height, which we can write as 25 meters squared or square meter times pi times height. And since we are asked to find for dH dt, that means that, and also because V and H are functions of time, so we use the chain rule to compute for dV dt and dH dt. We compute the derivative with respect to time of both sides. So we have the d dt of V and d dt of 25 meters squared times pi times h. Okay, on the left hand side we have dV dt, while on the right hand side 25 meters squared pi is constant, so we can take it out of the dt. Then the derivative of height, no, with respect to time is dH dt. Okay, and since we're looking for dH dt, we must isolate this. Okay, after substituting the given. So your dV dt is, what is your dV dt? dV dt is 3 meters cubic meter per minute. You have 25 meters squared pi dH dt. You're solving for dH dt, so you divide both sides by 25 meters squared pi. Okay, so you have 3 cubic meters per minute over 25 meters squared times pi plus dH dt. It means that your dH dt is the meter squared here, and that one will cancel, so you are left with meter per minute. So your dH dt is 3 over 25 pi meter per minute. Again, what is the implication of this? It means that the height of the water is increasing, no, at the rate of 3 over 25 pi meters per minute. Okay, so that's for our third example.